Can you see my slides?
Yes, looks good.
Okay, great. Thanks for the introduction again, Yongchen. So basically, today I want to talk about the idea of restoring smoothness from discretized non-smoothness in numerical simulations, in FEM in our case. And to make it more concrete, I am going to focus on this new recent research we did. It's kind of one of the most non-smooth problems in solid mechanics, which is frictional contact. So before talking about that, let me first give an overview of what I work on in general. So like you just said, I work a lot for computer graphics because of Hollywood. And it overall looks at continuum mechanics and numerical PDEs. For example, we had this project on elastoplasticity and fracture, simulating breaking bread, and fluid dynamics for incompressible flow, and multi-phase particle fluid mixture, like things for sediment transportation, water sand injection. Also investigate numerical aspects like domain decomposition, multi-grid solvers to increase the efficiency, and also HPC, high performance computing aspects like multi-GPU parallelization, exascale computing on supercomputers. And those are usually for graphics, and beyond graphics, we also do broad applied science and engineering. For example, computational geomechanics, like simulating this, predicting this avalanche triggering by a skier, and compare with explosives in the real world. And also biomechanics for surgery training and surgical planning, computer vision stuff with photorealistic rendering. This is really for machine learning and reconstruction purposes, topology optimization, and also nowadays more AI machine learning and inverse problems in robotics, such as like designing a soft aerial vehicle, a soft drone for particular purposes. But today I'll focus on projects on large deformation elastodynamics. So the question to answer is how to solve contact by changing this contact problem into a smooth problem. So I'm going to start with discussing the general non-contact elastodynamics with a nonlinear optimization-based integrator through this thing called incremental potential. And this basically allows us to simulate large deformation with really huge time steps. Then I'll illustrate this new approach for doing a variation of frictional contact. Basically simulate extremely challenging problems in FEM with contact mechanics. Lastly, I will extend the contact approach to arbitrary codimension manifolds like shells, rods, and even particles. So let's start with elastodynamics. We all know elastodynamics is for solids, and solids are everywhere in our daily life, from food, furniture, garments, to cars, architecture, and animals. So, and being able to simulate solids is allow us to create realistic visual effects and animations. And it also benefits many research and industrial fields, fashion design, biomechanics, robotics, engineering, material science for nanostructures. So in many of these areas, simulation will serve as a verification or validation process to help the design process before real-world experiments. So when we look at simulation of Lagrangian solids, we usually do it through time stepping, which discretizes time into small intervals and compute the displacement for the solid object of continuum. For maintaining stability, usually we do time integration. These are nonlinear problems, so often it requires many small time steps. This results in more solves, which can be very expensive for nonlinear problems. And for us, for graphics, it will be ideal if we can take frame rate time step sizes. Basically meaning if you are gonna play a video by with every frame separated by 1/24 seconds, like for movies, you want your time step size to be 1/24 as well. You do not want to take any substep. That's too costly for such applications. In computer graphics, for stability, we usually do backward Euler. So on a 3D Lagrangian mesh, like this 3D model, we basically, if you do linear FEM, we use a tetrahedron mesh to form this linear FEM space. And during the simulation, we maintain the connectivity and change the positions of the points. We compute the displacement of the points. Just standard FEM stuff. Then algebraically, you can stack all the 3D positions together as a column vector and do the same for the velocities. Then with the initial position and velocity, x0 and v0, if you do backward Euler, then you get these update rules for the simulation. So here, H is time step size, M is a mass matrix, F is internal elastic force. So this results in a nonlinear system of equations in terms of positions. And it's quite standard in engineering, in math, in graphics to just solve it with Newton's method for root finding. If we restrict our discussion to hyperelasticity, basically, if we assume the force comes from the gradient of elastic energy potential, then this whole system can actually be reformulated into a variational form. It's actually an optimization, unconstrained optimization problem. Basically, if you optimize the mass weighted 2 norm squared of your position, subtract a predictive position x tilde plus the potential energy term, then your optimality condition will give you back the root finding problem. So you can convert this root finding into a minimization problem. And so this is often called the variational or optimization-based time integrator for elastodynamics. It was invented in the 90s. The objective function here is called the incremental potential. And by choosing different parameters, you basically can convert a large group of integrators, including backward Euler, implicit midpoint, Newmark integrators, into this minimization form. So here, for simplicity, we'll focus on backward Euler. The first term is really called the inertia term. So it only exists for elastodynamics. You can eliminate this term if you want to do elastostatics. If you want to solve a static problem, force equilibrium. And the second term corresponds to hyperelasticity. This one is no longer convex or quadratic. This is highly nonlinear and non-convex. Say you're taking a pretty realistic elasticity model. And it also depends on your definition. So especially under large deformation or high-speed dynamics, this is very nonlinear. And since this second term is scaled by time step size squared, if you want to take a large time step size, the elasticity term becomes more dominant and the optimization becomes even worse conditioned. So without solving the optimization to convergence, numerical instabilities will happen, and visually it will be things like this. Therefore, it has been a long-standing goal to achieve robustness and stability guarantees in hard cases and large steps. We want these guarantees so that, say, like practitioners, artists can really play with the model in using their imagination to do things they want without worrying about the simulation going crazy. So more specifically, to maintain robustness, we can solve the optimization with line search. So line search methods optimize by searching along the descent directions of the objective, and then it's computed by back-solving energy gradients with proxy matrices, PI, in each optimization iteration. And different methods will differ in the proxy choice. For example, you can do limited memory BFGS as a quasi-Newton method. You can approximate the hashing with curvature information from previous iterates. And we can also be creative in designing the initial hashing approximation. For example, using approximate elasticity hashing from previous time steps, or even use the Laplacian matrix from the material space. And what we can also use a more accurate way is to just do standard projected Newton's method, projecting the actual hashing to SPD so that it can guarantee a descent direction. And by doing this, we will get global convergence guarantees for Newton's method for optimization. And even if you just do a simple backtracking line search, the only criterion is to search so that your energy decreases. And for finite elements hyperelasticity, since the global hashing matrix is assembled from element-wise stiffness matrix, all we need to do is to do the SPD projection on each local stiffness matrix by modifying its eigenvalues. So it's very efficient to do in practice and can be parallelized over the elements. Now with this incremental potential formulation, we can basically perform solid simulation, FEM solids, with basically arbitrarily large time step sizes on any arbitrarily extreme deformations over a wide range of shapes, models, and different material parameters. So this is nice. However, without simulating the collision and contact between the touching elastic bodies, the applicable scenarios are quite limited. Basically, you take a model, you stretch and squash, like you see here. It's not useful enough. So next, I'll discuss this new variation of frictional contact approach. It's built on top of this, the previous incremental potential formulation. And briefly speaking, elastodynamics with contact is very challenging. If you did any contact mechanics, you know how difficult those things can become. And there's a lot of literature in both computer graphics and computational mechanics on modeling contact. And for almost all existing methods, small time step sizes are required to avoid failures like interpenetration and numerical instability. And furthermore, existing methods, they usually also require, for example, numerical parameter tuning when you change the geometry, change the stiffness, or change time step size. So different tolerances, different iteration counts, different empirical parameters. It's really painful with the existing methods, with a lot of existing methods. So to address these challenges, we propose this new method called incremental potential contact, or IPC. Basically, we want to really guarantee intersection-free states and parameter tuning-free simulations. So we target at really challenging cases, and we need stable and accurate simulations with as few parameters as possible. So as just mentioned, the elastic potential without contact is already nonlinear and non-convex. That makes the optimization problem hard to solve. And now contact adds extra complex constraints to the optimization problem. Basically, these constraints will prevent objects from interpenetrating. There are two major challenges result from adding this inequality constraint. First, what this GX function, what it should be, is already hard to define in a consistent way for discrete 3D surfaces. And the other challenge here is that how to solve this inequality constraint problem with both the objective function and the constraint function. They're both nonlinear and non-convex. In traditional methods, to define this constraint function G, one choice is to require a non-negative signed volume for the geometry formed by closest pairs, like this point A pair. Another popular definition is to require the signed distance between closest points in the normal direction to be non-negative. Then many existing methods will compute the constraint set once per time step and adopt sequential quadratic programming or SQP type methods. And so the SQP iteratively linearizes both the objective function and the constraint until convergence. But even if it's converged, these constraint definitions, they really rely on small displacement. When the displacement is large, like the two examples here, even though things are not colliding, the constraints are still violated. So together with the constraint linearization, the solver becomes even more inaccurate. And sometimes in practice, things are over-constrained, you get locking, and some other times penetration still happens easily, even though the constraint is satisfied. So therefore, to alleviate these issues, many methods often have heuristic constraint set updating strategies and or run with very small time step sizes just to improve the stability. And in practice, especially in computer graphics, sometimes people just do like for efficiency, they apply a single iteration, so that further hurts the stability and accuracy. And in addition, heuristic constraint offsets are often applied to help reduce the interpenetrations and failures. But despite all these cares, we compare with some state-of-the-art FEM packages and also commercial softwares, they could still fail easily as we vary setups, as we make the contact situations more complex. And now let's move on to our new perspective. So first, we realize that the existing constraint definitions based on volumes or gaps, they're not globally valid. The key intuition we came up with is that continuously in time, we can always evaluate the unsigned distance between discrete surfaces. And that's a consistent measure for whether things glide. An unsigned distance is easy to compute. For example, finding the distance between a point and a triangle that has an analytical solution. Or for edge versus edge, when we're doing, say, thin rods, the distance also has an analytical solution. And what's even better is that these precise distances here in both cases, they're piecewise smooth functions. For example, in 2D, the point edge distance, it's just depending on whether the point is inside the span of the orthogonal span of the edge. It's just piecewise smooth expressions. So computing the distance is doable, but now the issue is that these unsigned distance, they're unsigned, so they're always non-negative. So how can we define an inequality constraint for collision? They're already like always satisfying. So the solution is quite simple, actually. We just need to remove the equality part. In other words, we require the unsigned distance between things to always be positive. And this needs to hold true continuously in time. So now, given an intersection for initial configuration, if each solver iteration, and let's look at the updating trajectory of all the geometry, all the point triangle pairs and all the edge pairs. Now, if every point on the trajectory remains strictly non-zero unsigned distance, so they're strictly never touching each other continuously in time, if we can guarantee that, then this entire simulation will be guaranteed to be still strictly intersection-free, interpenetration-free. So, and this constraint definition, since it's based on unsigned distance, we can generalize it onto codimensional objects like sharp, thin plates, or even needles, which is impossible to define signed distances or signed volumes. Now, getting back to the constraint definition, so for each iteration I in the nonlinear optimization, the configuration update, we can imagine it's a linear trajectory from xi to xi plus 1. And we can conduct this computation called continuous collision detection, or CCD. Basically, CCD is a small routine to find the smallest step size, alpha CCD here, the smallest ratio of this trajectory, so that it first brings any distance to 0. So for example, in this drawing here, if the red point is crossing this green edge, as this trajectory, then CCD will return something like 1/3. So that's the first time they will actually collide. And in reality, for 3D geometry, CCD computation corresponds to finding the smallest positive root of a cubic equation for time, and that can be solved quite easily. Then after we find the CCD step size, as long as we make sure that the optimization step size is bounded by this CCD step size, then our optimization step in this situation will not really break the positive distance constraint. And this is often called line search filtering. Basically, you filter the step size upper bound for line search so that you prevent things from happening. This idea has been used in interior point methods. And I think we're the first to bring it into standard Newton's method. Now for the optimization, recall that another issue for the SQP-based methods is that you have to linearize the constraints. So to avoid linearization, we use the barrier method. We're okay with the nonlinearity. We use the barrier method to handle the inequality constraint. And when the distance is approaching 0, the barrier goes to infinity. So it will provide a large enough force to avoid interpenetration. And using barriers essentially reduces the inequality constraint problem into an unconstrained problem. And so you can apply line search, you can evaluate the energy, you can do everything to ensure stability and global convergence. And with Newton's method, so each Newton iteration is a linearization. But the original constraints are not linearized because when Newton converges, you're solving exactly the original problem. So it's unlike SQP, you're really changing the original problem, you're linearizing the problem. So Newton is way better. Okay, so now so far we're doing barriers, but practically we have another issue, which is that we're doing collisions. So the number of primitive pairs is quadratically increasing with the number of your surface primitives. So this makes things intractable at high resolution. And the main issue here is that the support of the barrier function with a log is globally defined. That means no matter how far away things are, there's still a tiny energy associated with it. So the straightforward solution is to clamp it. So you find the threshold, a distance threshold, we name it d hat. So we only apply contact forces when primitives get closer than d hat. But unfortunately, this is simple, but this clamped log function, it's C0, it's not even smooth. And using a non-smooth objective function for Newton's method, or for any gradient-based optimization, it's gonna harm the convergence a lot. So therefore, the main idea here from us is to reformulate a smooth version. And we do it by applying a modification here to smooth the clamping point up to C2 continuous. So it still filters out far away primitive pairs. And when we use a smaller threshold, the smooth function approximation is getting, it will like reduce back to the original non-smooth contact problem with high accuracy. So of course, when the threshold gets smaller, the curve becomes sharper and the optimization becomes more expensive, but this can be treated as a controllable trade-off. So for computer graphics, for visual effects animations, usually we use this threshold, we use 1 millimeter distance for something that's like 1 meter large, 1 meter wide. And visually, you cannot really tell that there's a gap like 1 millimeter. And for mechanical applications where accuracy matters more, we can even go all the way down to, say, 10 to the minus 10 meters without any problem. Now, this C2 smoothly clamped barrier makes optimization really efficient. So because you can skip far away primitive pairs. So here we show our largest scale example. This is made with more than 2 million tetrahedra. And look at how intricate the contact is. None of these deformable tentacles are intersected, and none of the elements are inverted. So this simulation costs around only 5 minutes per time step on a single MacBook. Okay, so next we can evaluate the accuracy of the barrier method. So for nonlinear optimization, there are 4 KKT conditions for the optimality. That include primal feasibility. That corresponds to the constraint that the interpenetration free constraint here. Then there's dual feasibility, corresponding to the requirement that the contact force can only push but not pull. And next, stationarity condition for this is just momentum balance. And finally, complementarity ensures that the contact force is only applied on regions that are actually touching. So in our setting, primal and dual feasibility, they're satisfied by construction directly from the distance formula. Stationarity accuracy can be controlled by the Newton tolerance. And the complementarity slackness, this can be controlled by the clamping threshold, the distance threshold, because only pairs that are closer than this D hat parameter, they will have a non-zero contact force. So what's really exciting here is that the accuracy of force equilibrium, the momentum balance, and the contact complementarity, they're fully decoupled. And even if we request less accurate results, especially for graphics, there will still be no interpenetration or no pulling forces. So this gives us a lot of flexibility. Now here's a small test to get a sense of the tight accuracy. We can place a 1 meter wide cube above the slot that's only 2 microns wider. And using this small d hat, it's like 1e-6, we can successfully simulate the sliding through this tight fitting slot. Here's another cool example. So with elastic wave propagation shown for elastic body impact, which is a golf ball taken from high-speed recording. So all that's necessary here for the simulation was to plug in the experiment's original material and velocity parameters without any additional numerical parameters tuning. Okay, so that's a FEM elastodynamics solver with friction. Sorry, with intersection-free constraints. But the contact force is still along the normal direction. So next we have to consider friction. Friction is also non-smooth. In fact, it's not even non-smooth, it's discontinuous. And friction can be really derived from the maximum dissipation principle. I think we're gonna skip the details, but basically you can use a tangent operator T to compute a local 2D relative sliding displacement for a pair of geometry, and you can take the position vectors and map it to the 2D plane. Then the friction force can be defined in 2 cases, corresponding to dynamic and static friction. In the dynamic case, the sliding displacement, the relative velocity is non-zero, and friction is proportional to lambda, which is the normal force magnitude. And for static friction, we have this little F vector acting like a basis And this spaces can take any vector with length that's smaller than 1. So in the static friction case, when your relative velocity is 0, it can point to any direction. So, and from this little f, we know that we can clearly see some challenges already. So first, in the transition between the two modes, sliding and sticking, there will be a non-smooth jump in both the magnitude and the direction for the force. So the jumps are possible. And secondly, because of the sticking modes, the friction force is not really uniquely defined by displacements anymore until stationarity. Another challenge is that frictional contact force, if you compute its derivative, the Jacobian of this friction force is not symmetric. So it's not integrable. There's no well-defined potential energy whose gradient will generate the friction force. So this makes it really hard to incorporate friction into optimization. Now, to tackle these problems, we can look at friction. It's a non-smooth function in terms of displacement. Then, like the title of this talk, we want to smooth things out. So similarly to the contact treatment, we can smooth the friction displacement curve with some controlled and bounded accuracy. So here, the blue line is the original friction displacement relation. So as you can see, when displacement is 0, friction can be anywhere. And we smoothed it by picking another velocity threshold, this epsilon v here in the slide, so that if the velocity is smaller than this velocity threshold, we view it as sticking. Then we use a C1 continuous function to connect the dynamic and static friction region, connect those two transition points. And this basically the regularized curve, it forms a bijective map from the velocity magnitudes to friction magnitudes for any velocities below the limits. Then, in order to apply friction as a potential energy for the optimization problem, we have to modify the force a little bit. Basically, you can do it sort of like semi-implicit. You can discretize the sliding basis, the T operator, as well as the normal force, lambda. You discretize them, you lag them to the previous iteration. And then by treating them as a constant, then the friction force become integrable. So you can integrate the friction force to find a smooth potential energy. And this allows us to define a smooth dissipative potential for the friction. And this can be consistently integrated into the Newton type solver. And in practice, it's like a fixed point iteration for the normal force and the tangent operator. We can add another iteration beyond the Newton loop so that eventually everything converges. It is still converging to the accurate solution to the original problem. Okay, so let's look at some videos. With friction, we can simulate this stable structure. It's called the masonry arch. It's made with stiff cement materials. We take the cement Young's modulus, Poisson's ratio, density, and it's maintaining its structure due to all those static frictions. And also for the stable structure of a stiff board house, like with poker cards. And if we heat it with some high-speed boxes, we can see that there's this transition between sticking and sliding modes, and those can be naturally resolved. And this chain example, so with our IPC, we can robustly simulate the chain with 10 links without any interpenetration. So the setup looks simple, but it's actually very challenging for contact solvers. Because of the accumulated force loads. And in fact, we can add as many links as we want. The optimization integrator with line search guarantees that our solver will converge. And here is a twisting rod example. These rods are not real rods, they are made of tetrahedra. so that we can see the cool buckling. Basically, we continue this rod simulation for 100 seconds so that we could see a lot of knots and extreme deformations, and our method stays robust and efficient. Now, we are professors, so if you played with dotted clouds with chunks, you may know the famous stick-slip instability. Our friction model can actually capture that. And even with large deformation, we can see that the left leg of this 3D model is oscillating between stick and slip before rolling down. This is what happens when you have a large frictional coefficient. Okay, so far all these simulations are done with volumetric bodies. Now for linear finite elements, every example so far you saw they're discretized with tetrahedral mesh. And next, I'll briefly cover some extra ingredients, extending the contact model onto codimensional structures like shells and rods. So the frictional contact is barrier energies on the surface. So we can directly try it on shells. So here we're simulating a cloth fabric, and we twist it. The cloth is discretized with a triangle mesh, and apparently something is not quite right here. So it's the thickness value of the shell that's getting ignored. So you do not see reasonable buckling or knots that should be formed when you twist a cloth material in the real world. So the question is, can we capture it by modifying the contact handling method so that the mid surface of the shell are always apart by a non-zero distance, which be interpreted as a finite thickness. So as mentioned earlier, some existing methods also do some constraint offset, but they mostly do it for avoiding instability. So to see how that offset models thickness, we did a test on state-of-the-art fabric solver, and we dropped 10 pieces of cloth onto a fixed board and set the constraint offset to different values. So, and what we observed is that we have to use 1 millisecond time step size to avoid interpenetration. Then when we use 10 millimeters, we obtain a higher stack, which is great, as if the cloth is thicker. But when we test 1 millimeters for thinner cloth, the intersection artifact happens again. This is basically one of the several benchmarks we did to show that it's extremely impossible to find the optimal time step size so that you don't have interpenetration and it captures the thickness of the shell. Now we test that on our contact formulation. Since this d-hat threshold defines the range of collision forces, we can even understand it like a one-dimensional elastic constitutive model along the thickness direction. So by using different d-hat values, we can successfully simulate this cross stack example with arbitrarily large time step size, 0.04 here. And the result has no interpenetration or artifacts and provides a way to control the thickness. And since the contact force changes with distance, we can also capture the indentation effects when we drop a ball onto the cloth stack. Now, furthermore, it's also possible to introduce a constraint offset in the barrier function to provide an inelastic thickness modeling. So this inelastic thickness will ensure that objects are guaranteed to be separated at a certain finite value. And to do that, we just need to subtract some thickness value from the distance inside the barrier function. This actually directly fits the class tube twisting example. It will form bell-shaped knots in the middle. And as we twist long enough, the nice buckling behaviors are also captured in a more, I would say it's a visually plausible way, physically convincing way. It's like if you take a tower and twist it in the real world. Now, being able to model accurate thickness also allows us to simulate many more effects that are never achieved before in mechanics or graphics. For example, to simulate card shuffling. The challenges here exist in both the stiffness bending behavior and the correct thickness modeling. So these are necessary for the pile of 52 cards to have the correct height, in addition to all the challenges in the frictional contact. And we can, for the first time, capture all these intricate behaviors and reproduce the deck height matching the real world. We can also simulate multi-layer garment with a carry sequence as a boundary condition. So such simulations are not only ubiquitous in movies, animations, video games, but also they play a critical role in fashion design. And there's also a fascinating rising industry with a huge market, like for virtual clothing try-ons in combination with AR, VR, and computer vision technology. Basically, when you buy clothes, you can, if the customer has your 3D model scanned, then you can try different variations of clothing directly using animations. And we can also simulate rods or hairs using a discrete rod model to capture bending and twisting. So here, for the hair simulation, at the maximum, we process over 1 million contact stencils per time step. And beyond hairs, we can also simulate noodles. They're pretty thick rods. And because the thickness is modeled with guarantees, we can also easily visualize the surface by just assign a cylinder to each segment. And we can also simulate sprinkles by representing each sprinkle as a single segment with 2 nodes. Then in the codimension 3 case, we can also simulate 1D objects in 3D, basically spherical sand particles, by treating each sand grain as a single vertex, a single point. Then our framework handles a point-to-point frictional contact. And finally, we put everything together. Here at the bottom, we create a net formed by discrete rods, and we drop a volumetric body and a cloth and some sand particles. Okay, so to summarize the framework, building on top of the incremental potential concept, IPC is the first unconditionally robust and accurate contact handling framework. It has friction and fully implicit nonlinear elasto dynamics. It guarantees interpenetration-free trajectories, and it supports a spectrum of codimensions. Now, based on the foundations from nonlinear optimization, IPC also provides a controllable trade-off between efficiency and accuracy for different application scenarios. We also performed a lot of experiments and benchmark studies. And for practitioners, the framework really frees designers, engineers, and artists from extensive algorithmic parameter tuning, and it enables brand new phenomenon to be easily simulated. And going back to the high level of this talk, like in the very beginning, I think we can develop ways to regularize things, to restore the smoothness for many non-smooth or discontinuous physical process. The frictional contact is a good example, but we can further apply this philosophy to many other problems, such as plasticity, fracture, phase change, and so on. Here are the acknowledgements, and thank you for your attention.
Yeah, thank you.